Hi, my name's Bob Grinier and I'm a volunteer with Martin Fleischmann Memorial Project. So welcome everyone to this presentation, How Could Parkhomov's 225-day reactor get started and keep running even after the nickel had melted? Well, this is a question that I have wanted to give you the answer to, as far as I'm concerned, for many moons. In fact, the time that I kind of hinted towards it was at ICCF 22 in Italy. And I was asked a number of questions, and I wasn't fully on board with my thinking at that time, but since then everything I think has fallen into place, and hopefully with the grounding that I've been sharing with you over the last several years, that you will be able to really see that this is how it is, and also you will understand that this probably is how the nickel powder reactors of Rossi and of Thermocore back in the 1990s and many other systems like this would have worked. It would also give you explanation for Brian Ahern's patent application that I interviewed with him early on in the project's history, and also the words that I've recounted of Baranov and Zatelepin with their nickel powder research, which they stopped due to apparent production of exotic vacuum objects, also called strange radiation in their neutral form that they observed in their reaction in their experiments in Moscow. So I'm going to wait until a few people come into the room. Who have we got here? Thank you, Alan, for joining us today. I hope this will answer some mysteries over the last decade, basically, for our research. Hi Artifact, hi Simeon, and hi Cookie, great to have you in the house. FRCACC, whatever that is. I don't know. Derv, Rajput, and Shockwave, great. Okay, so hi. Okay, so what am I going to be talking about today? Well, if you can see on the slide here, on the left-hand side is some PNK02, I think it is, carbonyl nickel. This is not nickel carbonyl. Nickel carbonyl is very toxic. This is what gets left when nickel carbonyl kind of like deposits the nickel that it's carrying, and it becomes very pure nickel. It's one way of refining impure nickel because of the carbon monoxide reaction with nickel. It produces very pure nickel, and this has these dendritic structures, and this was taken by Bob Higgins, and it was shared at ICCF 22 as part of the presentation where I was presenting on behalf of Alexander Parkhomov. On the right here you see an example reactor with some example nickel in there. I say example because when I first saw this looked like it could be some alumina, or it could be some boron nitride tube, which I know he'd used before because he'd sent me samples, and there's reasons why you'd use that, which I've discussed in the past. But when I was doing the preparation work for the presentation, I found a lot of carbon, like a huge amount of carbon in the core, and I questioned Alexander Parkhomov about this, and I talk about it in the presentation that I gave, and he came back and admitted that actually it was silicon carbide in there. And this kind of changed the dynamics, because if you have a silicon carbide, what he found was the mass originally of calcium in the tube was actually only 1% to start with, but the mass after the experiment was around about 20%. And if you run the reaction tables and you fuse silicon and carbon together, where you have silicon is 28 and carbon is 12, you put those together, that makes you 40. So there we go. So you can get a lot of calcium from that. But what is it? What is it that is causing that thing to fuse? Well, could it be the thing that is all the same thing? Is it the exotic vacuum objects, the coherent matter, this ball lightning, this, how shall we put it, itonic clusters of Takaaki Matsumoto? Well, there's one phrase that I've been mentioning, or name for this, that I've mentioned a good number of times, and this presentation will be focusing on that. But before I go there, I want to talk about hi John, I want to talk about some context slides because I think they're very important, and they're just a little bit of a refresher of some of the things that we've discussed over the last couple of years. And I think maybe as we review this other work, it'll be like, aha, aha, aha. And you'll see why potentially I've been talking about these things in the order I have done, and really it's so that you understand the words in the sentence so you can understand the whole sentence. Hopefully that is my hope here. So hi John as well, so thank you those people that are joining us tonight. Okay, so like I say, you will have seen some of the slides before if you've been watching the MFMP's channel over the last couple of years, and I will just go and share those now. So this is the cover slide, and I want to talk about the Joseph Papp accident. And the reason I'm referring to this is because this is the this slide has a number of the relevant images on here of what I believe is a very similar effect going on, but also this is the first time I talked about Coulombic explosion, and it's interesting because I talked off the record, I guess, ICCF22 with a number of people, and it's interesting because there was some commentary at ICCF23 about Coulombic explosions, explaining cathode spots, and as if it's nothing special, and like they're kind of like shaped charge, and that is what an evo is. And it's like, kind of, I know what you're trying to do there, but actually you're missing the entire point. The actual things, these Coulombic explosions, they are actually making the active agents, and so that is kind of what we're going to be talking about in a roundabout way. So we in the Suhaus Ralkar foil making device, we found these structures on the nickel foil that was made, and this is a plasma flow discharge. So there's a water flow, and he's discharging I think it was a couple of thousand volts, 2100 volts at a certain frequency into and through the fluid that was raining down from the cathode to the anode. And we saw this structure here, which is very similar to the sort of structure we see here with S.V. Adamenko. And in S.V. Adamenko's work, this was at the Proton 21 labs in the old Soviet isotope factory just outside of Kiev. And I think this work started in 2000, 2001, and they were doing, I think, a 300 joule relativistic discharge. I think it was around about 1/10 of C. And I've talked about that in detail in the past. And so whatever, it had this little anode, and the electron beam would bunch into the tip of this anode and cause some exotic vacuum object loveliness, or they call it an electronucleon macrocluster, and you would have an explosion, and you would get a vast number of the elements in the periodic table instantaneously synthesized. And actually, interestingly, there were lumps that were high ratios of particular elements which were not in the starting material. And for those that like gold, they also made gold. And also on the Ralkar foil, we found gold, and I think it was palladium as well. Now, in the Hutchison sample here, it's obviously achieved through a very different way, but it's a similar effect, you can see. And then this is Papp's when he was I think working with the military and trying to make a cannon out of this, and this was the pipe, and I think this pipe was actually embedded in concrete, but this is what they observed. So I think they referred to this as cluster impact fusion before it was classified. But anyway, Joseph Papp accident. I talked about this in my monopole clutch video. In fact, several of the slides will be from the monopole clutch video, and you'll understand why in a minute. Okay, so there was a thin wire attached to the wall, insufficient to provide power. This was with the Papp's sort of mechanical energy generator, which also produced a lot of electrical energy via a magnetohydrodynamic coils, but they were just used to, that was just essentially mostly dumped into resistors and discarded. This was ground drain for excess exotic vacuum objects, I believe. So we already know from Russian work that you could send 25 kilowatts of effective of 25 kilowatts of something that would illuminate 25 kilowatts of tungsten light bulbs down an 8 micron wire. And so we already know that exotic vacuum objects from the early 1990s could travel en masse through very, very thin wires. So for me, it's no problem to see that excess evos, which will be created, whether he liked it or not and had a different opinion, they would have been created in his device. Rather than them, I believe, sitting in the metals and disrupting them, like you see with Hutchison here, and like you see, I believe, in the Papp explosion here and whatever else. You want to drain those. So I believe that that's what that was. And then the evos softened the metal of the engine cylinder because Feynman took out the wire, and it reached a critical threshold in the engine block. So we see with Hutchison metals, if they are magnetic, or high temperature, they will hold and hold and hold, and then they would just fracture. I believe that it was weakened to the point that the aplasmatic transition could not be contained. And I will talk about the Papp engine in extreme detail in coming presentations later in the year. And I have a very reasonably good understanding, I think, of what's going on there and how one can work with that. And a partner that wants to make his work open source as well. So anyway, the pressure of the plasmatic transition could not be contained, causing critical failure, and this led to the emission of something. And in Feynman's own account, he said a cone of silvery uniform stuff shot out and turned to smoke. Okay, so I'm going to go to that account, and I'm just going to first switch. You can see my ugly mug, and I will find that account, which I have somewhere in a web browser, if I can pull it up. Here, yes, we got it. No, not that one. That's for talking about something later. Okay. Okay. So, give me a second. And so, right, so this here was Richard Feynman on Papp Perpetual Motion Engine, as he liked to call it, originally published in the Laser Journal of Southern California Skeptics. And anyway, this is Richard Feynman's own account. And the paragraph I want to draw your attention to here is, okay, have the lead in. There were quite a few wires running from the engine down to where Mr. Papp used and the spectators were standing, into a set of instruments used for measurement. These included a variac, a variable transformer with a dial which would put out different voltages. The instruments were in turn connected by a cord to an electrical outlet in the side of the building, so it was pretty obvious where the power supply was coming from. This is Richard Feynman's account. The engine started to go around, and there was a bit of disappointment. The propeller of the fan went around quietly without the noise of an ordinary engine, with powerful explosions in the cylinders and everything. It looked very much like an electric motor. Mr. Papp pulled the plug from the wall, and the fan propeller continued to turn. "You see, this cord has nothing to do with the engine. It's only supplying power to the instruments," he said. "Well, that was easy. He's got a storage battery inside the engine. Do you mind if I hold the plug?" I asked. "Not at all," replied Mr. Papp, and he handed it to me. It wasn't very long before he asked me to give it back, so give me back the plug. "I'd like to hold it a little longer," I said, figuring that if I stalled around enough, the damn thing would stop. Pretty soon, Mr. Papp was frantic, so I, Richard Feynman, gave him back the plug, and he plugged it back into the wall. A few moments later, there was a big explosion. A cone of silvery, uniform stuff shot out and turned to smoke. The ruined engine fell over on its side. The man standing next to me said, "I've been hit." I looked at him, and the whole side of his arm was torn open. You could see all the muscle fibers, tendons and everything. Sorry, this is a bit gory, but anyway, you can read this in your own time. The key point here is, I believe that this was probably the cylinder, or the piston head, and maybe, let's say, made of aluminium. We know aluminium is greatly affected by exotic vacuum objects, and I think it turned into some jelly-like blob, and it came out, and metals that have been exposed to exotic vacuum objects tend to corrode very quickly. Well, what is corrosion? In this case, it's in interaction with the oxygen in the air, and I think what happened was they have an affinity for the oxygen that's vastly higher than normal aluminium would do. And we already know aluminium really likes to be oxidized. If you've ever got an aluminium pan and you've scraped it, you'll see that the oxide layer forms very quickly. So imagine that to the nth degree, and you get, in my view, a Coulombic explosion. So I believe that's what's going on there. So this was the first time when I was talking about this that I mentioned that there was probably something like a Coulombic explosion involved with the initiation of some LENR processes or material that had exotic vacuum objects in them. Okay, okay. So we'll go back to the presentation here. So, the other data points I want to draw your attention to are this one, which is exploding wires. This was going to be very relevant in a few minutes. And the exploding wires in Leonid Oritskev, I think this was at Moscow National Physics Laboratory, or no, at the Kurchatov Institute, actually, in Moscow. I think he conducted the initial tests here. And this ball lightning you see here, which is also reflected again from above in this mirror. So you've got a direct view and a top-down view of this ball lightning, which has come out of the chamber. So the explosion isn't here. The explosion's inside the chamber, but on a number of the events, they would see these plasma structures appearing outside of the reactor. Okay. Now, could it be because the lead wires allowed whatever it was, these same things that I'm saying are able to travel down wires in the Feynman account, or not his account saying they're going down the wires, but I'm saying that it's going down the wires. Could that be what's going on here? I'm not so interested in that aspect of it. I'm interested in the fact that this is exploding foils. We know that this does transmutation every day of the week, and that what he observed were these magnetic monopoles going on to iron 57, and the account of how he proved that using NMR process. It's given in this link down the bottom here, and you can go and read that paper. Okay, so that's one data point. That is exploding foils leading to magnetic monopoles, and these magnetic monopoles would appear to be, in some accounts, cold neutrino condensates, which are neutral and they can travel great distances. And in fact, what he had was the iron 57 foils were 70 centimeters away from the tank, from the container, and the foil was exploding inside water, inside I think a polymer, inside metal, and then there's 70 centimeters of air. So whatever this radiation was that's able to change the magnetic fine moment of the iron 57 was able to travel through all those materials and through that air. So that has to be borne in mind. And then I want to refer to this figure. The energy of colliding particles should be on the order of 0.5 eV or higher in order to create cold neutrinos. So we've got something here where these are cold neutrino condensates, or magnetically excited cold neutrinos. So those can be synthesized. And so what we're looking for is, in the exploding thing, for the energy to go above 0.5 EV, and then we're going to start creating the things that are actually observed by multiple parties. And the result of these things going into beta isotopes is inverse beta decay, which itself can lead to the production of monochromatic beta particles, as I discussed in my previous presentation. Okay, so hopefully you can start to see all of these little nuggets coming together, and it's a really special thing to be at this stage in the conversation right now, and hopefully there's a good number of you out there that gets it and why it's important and so forth. So and if you're, for instance, at 5,100 Kelvin, you've got over 50% of the matter in whatever it is, the matter, participating in the production of cold neutrinos. Okay, so there's a whole bunch of other data points that I'm going to run through very quickly in this next slide. And after a couple of other slides, what we're going to do is we're going to read a particular paper. And I've actually only read through half of it this evening. The other half I'll just read with you real time and drag out points. I read it probably 2 years ago last. Actually, no, the last time I probably read it was May 20th last year. But anyway, I'll go through that with you. But I think by the time we've gone through the first few pages, you go, oh my God, okay, right, I understand it now, hopefully. Okay, so back to the slide here. These are a couple of data points I want to throw at you. Hutchison samples changed over time, and this was from 1979, from when he first started doing his work. We're going to have some slides from the monopole clutch, which I think will detail these next couple of points. Piantelli's nickel rod was active 2 months after being removed from the reactor in 1996, and this was from the reactor that produced the highest energy output from any Piantelli, Sergio Ficcardi. So this is Francesco Piantelli, Professor Francesco Piantelli from University di Siena, and Professor Sergio Ficcardi from University di Bologna, who was an amazing nuclear expert. So they worked on this together, and this particular reactor was the one that produced neutrons, and that was from the interaction of protons with vanadium-50. Anyway, that aside, after they got the rod back, I think it was 3 weeks later, they got the rod back from the nuclear authority, and a number of weeks after that, they put it into a cloud chamber. And you'll see that in the next slide. Ken Shoulders said that exotic vacuum objects can live in metals indefinitely. Okay, so he had said this much earlier in other writings, but in the transcript of the interview with him and John Hutchison, which I transcribed, and you can see, and I've talked about this in other channels that I've published in the past. This was in 2010. So he's saying that these exotic vacuum objects, once they're produced, they can live in metals indefinitely. And in fact, he goes on to say in that statement that unless I intentionally blow them up. Okay. John Dash et al. And Irina Savatamova et al. They both saw elemental and morphological shifts over time, so supporting John Hutchison's observations from the late 70s and early 80s. This, I think I'm right in saying it's John Dash, but certainly Irina Savatamova. I think these are best discussed in papers by Ed Lewis. I think he might even have talked about it in ICCF 23, but he's talked about it a good number of times. Anyway, you can go and look at through the Lena Events database on nanosoft.co.nz and look into these people and those papers that might show that. Lyon observed tracks on his X-ray film 9 months after reheating copper oxide crusts from Lyon 1, and this was in early 2018. He reheated it, but it was done in, I think June 2017 that he actually did the original Lyon reactor. So what it's implying here is that you could re-energize the structures that were in the copper. And we know the copper oxide. We know 100% that they were in there because we saw those beautiful Lyon tracks, the first strange radiation tracks we observed in Lyon material, right there in the active in the crust on the outside of the reactor. So we know that they were in there, and he was able to reactivate some that were in there. Baranov, and when I was talking about this in Sochi in October 2018 to Baranov and Zatalepin, they said they observed reactivation, I think it was in their bismuth salts, 18 months later. and this was a personal recollection to me. Basically, we've gone more than 9 months. We've done 18 months, and they actually published that, I think, in 2019, and I've published the video where that was discussed. And in that video where they discussed it, they saw this strange radiation track, and it's nearly identical to one of the strange radiation coherent matter traveling waves that was produced in a Vega reactor, in this case by David, and picked it out of some of his videos. By the way, we've got some other excellent videos and some important data. Don't let me forget. I must do a presentation on that. Anyway, and then Bogdanovich et al. Reported recording of glowing moving toroids on metal targets, and this is in a peer-reviewed paper from the Moscow Nuclear Physics Institute 2 days after plasma flow discharge. So remember the plasma flow discharge where we had these elements synthesized from Suhas-Ralka? Well, this is plasma flow discharge, very similar, but they're observing 2 days later actual glowing things, toroids moving around on a piece of metal. And when this was recounted to another party, they said, "Oh, this sounds a bit like some classified work that was where we were doing electron beam processing of some metal landing gear in the 70s or whatever, and we found these little glowing spots on the landing gear, and we just brushed them off with a wire brush." Because we didn't know what they were. I think it was in the 80s maybe. And the person investigated as to whether there was any further investigation going on about that subsequent to the Bogdanovich et al. Report. And they said, well, actually, we found these glowing things still glowing 2 months later. 2 months later. So this is very similar to the claims of Piantelli, where something was creating this. There was creating these very high energy emissions. And so nevertheless, on having observed tracks of up to 9 centimeters, alpha particles can be ruled out. In fact, alpha particles of this range would have an energy of about 20 mega electron volts, which is too high for alpha emissions from known radioactive elements. So this is not possible. So I think it's 6.7 mega electron volt protons, which is what is being observed here. As I've said before, this was a key piece of data to show that firstly, the structures can persist in metals. This is 2 months later, and that there's a rounding error, and when it's doing transmutation, I believe the rounding error, the most likely one is protons. So people who are doing Lena experiments may often find that they see excess hydrogen. The excess hydrogen, in my view, comes from this rounding error of transmutations because it's a fermion, it gets emitted out. Tritons also, which as I've discussed is the only radioactive element you get unless you force it all the way past lead and start getting things that fission back. So generally tritium is the only thing that it will produce because it's not helium, and so it gets produced. And that's why we have it in the Parkhomov reaction tables and on special request, but also so we can do the reactions for cleaning it up as well. Anyway, so and I think the excess hydrogen was first observed by Irving Langmuir in the early 1910s in his development of the tungsten filament light bulb. And so anyway, that's just an aside there. So this is running for 2 months after, and bearing in mind this is cold, so this is at room temperature, and I'll show you. This is cold, it's at room temperature, and it's emitting these, I think it's 6.7 or 7.6, is one or the other. Let's say it's at least 6.7 mega electron volt protons, and Piantelli's whole patent family is based on the protons being emitted into other receiver elements, preferentially lithium-7 going through the beryllium-8 decay to 2,4 helium line, or the boron-11 to carbon-12, both aneutronic reactions. Obviously the first one is the first fusion-fission, which proved that Einstein was correct in saying that this was possible, and it was done by Cockcroft and Walton, I think at the Cambridge Laboratory in 1932, for which they both won the Nobel Prize. Okay, I shared the Nobel Prize because you can only have 2 people winning it. Okay, so that is the Piantelli work, and then I also talked
about the Svyatomenko, where he observed these things that were eating the primary ions that they were firing in their secondary ion mass spectrometer. And this again was observed, I think, 12 times, he says. And this is long after they had done the discharge, which I described earlier. And then I want to give you an example of what I believe you have all seen in experiments that we have conducted, which is the work that we did with Royston Amarza gas and a titanium plate and some polytetrafluoroethylene. And I have this video here. There will be no audio, but I think you've seen it before. So that explosion... And that explosion removed a very large amount of the titanium in a very small period of time. And that when we looked at this is the PTFE on the right, this is the titanium. And these are the crystals that were observed on that titanium. And if we go on the Alan at Magic Sounds SEM, you can see here these crystals. And they are absolutely beautiful, pure dendritic titanium crystals with... cutoffs, like the cutoff is in the plasmoid that maybe formed them. And this is a very, very important sign in my overall picture of what is going on with these things, because if you go to the Solin pattern, again this is from the monopole clutch, Solin patterns, the physical processes in this substance are similar to those that occur in a superfluid, superconducting nuclear plasma neutron stars. So he's saying that basically what we are creating in the this coherent matter nuclear reactor, which is the basis for his December 1992 awarded patent application. He says that they obey the laws of Bose condensates and act as a classical coherent wave. So here you have that this is Bose condensates, it's Bose condensates, and it is classical coherent waves. So we've talked about coherent matter waves, and we've talked about condensation of the matter. Solin had it all, but just, it's a Russian pattern, and it wasn't available, and it took me years to see the significance of it and to actually bother to find it and then bother to translate it and then go, oh my God, he's done everything. That was August the 22nd or something last year. Anyway, therefore, it is detected spontaneously without... So basically, you don't have to do work to find out whether you've got a coherent matter nuclear reactor, because you can spontaneously see it without any chemical etching of nuclear fusion product due to the implementation of coherent, ultra-fast explosive crystallization. Coherent crystallization. It consists of many fragments and dispersed areas in the form of ordered clusters of microcrystals. Ordered clusters of microcrystals which are separated from each other by voids. So, what do we see here? I would call that pretty explosive. And if we look at it, I would argue that this really is here, which is in the focus of the explosion location. This is pure crystals of nickel, and we've shown that there are plasmoid structures coming off those. And they are with voids. They have voids in them. There's voids everywhere. Because if you have a normal melt, what happens is the dendrites grow and then they get backfilled. So, again, therefore it's detected spontaneously, i.e. you can see that this works without chemical etching of the nuclear fusion product due to the implementation of coherent, ultra-fast explosive. Well, that's pretty exactly what we saw, crystallization. It consists of many fragments and dispersed areas in the form ordered clusters of microcrystals, which are separated from each other by voids. Okay. So that is my background for this. Does anyone have any questions at this point? Does anyone want something gone over? Can everyone hear me? I didn't actually ask that. What I've done actually is I had got an air conditioning unit in today, and I froze the room before doing the presentation. I have a backup camera as well, so hopefully it won't fail like it was doing the other day because of overheating. It was 34 degrees yesterday and 33 I think today. Okay, volume fine, camera's up, got a backup camera. Okay, so we're going to go to the next key part of what I want to show you tonight. So just before I do that, I will remind you of these two slides. This one, where we have exploding foils producing magnetic monopoles in the form of what the Russians call string vortex solitons, which are the neutral form of magnetotoroelectrical radiation. And these are, in this case, they are clusters of cold neutrinos, possibly because of what they do to beta isotopes, and they can carry ions of material which they travel through, and this was proven by determining the depth and width of pits in some celluloid film, so they could actually show that there was a direct relationship with a factor. So this one, and then this one is very important as well. This 0.5 eV or higher will create a neutrino antineutrino pair, and that is very, very important. Okay, and you need solid, liquid, or dense plasma in order to do that. And electrons themselves will collide with atoms. In metals, in a 1 centimeter cube, there are about 10 to the 36 collisions per second. So there's plenty of opportunity for these things to occur. Okay, all right. Okay, so question: how is time a factor in evo production? I think you're going to have an answer to that today. Basically, the quicker you can get as much current into a small space before it blows up, you're going to have the better chance of forming exotic vacuum objects. And once they're kind of formed, you want some ions in there, ideally, to make them stable. Yeah, it does look exactly like tree moss. Okay, so let me go to this PDF now. Okay, and as usual, I will put the content that I'm talking about here into the presentation later. So into the remote view.icu. So here we have, I'm going to just quickly run over a couple of slides from Parkhomov. So this is the dual eye image, stereoscopic image that was shared, and I've given a link to that presentation. The key point here is that he saw excess heat, the peak of excess heat being relatively quickly after the reactor was started, and then over the 7 months it went down. It was a peak of copper of 3.6 for about 6 hours, and then it kind of like tailed off, and then for the longest time it was not so high, with an excess of around about 550 watts here, COP 2.5 here, and so forth. But after a period of time it dropped down, and he actually tried to put in hydrogen many months later to see if it would do anything extra, and it kind of basically went up, but that might just be a pressure related thing, and it then just fell down, and again the hydrogen did nothing. So the concept therefore is that something in my view, and my answer to the questions at the time were, something is made in the nickel when it's in this state, which persists and does transmutation regardless of when the nickel is melted. So
I consider that there's some birthing of something going on. And if you look at these things, they're dendritic themselves, but they're very pointy. They're very pointy, like a sharp, pointy arrow or a sharp, pointy spine from a porcupine, and they're very pointy, and they're also quite gappy, aren't they? They're like lots of crevices going on. Just consider what you are looking at here as we look at some other presentations and some papers this evening. Okay, so the good thing about this Russian paper here is that it is translated. So this was actually given at the what's that? 17th International Symposium on Discharges and Electrical Insulation in Vacuum, Berkeley, 1996. And I think the story goes here. Now, who am I talking about here? I've mentioned this guy a number of times, but I've never gone into him because I wanted to build the framework so you understood why this guy's work is so important. And the name is, I think it's George, or I think it's G. Mesiats. I have mentioned him many times. And he's from the Institute of Electrophysics, Russian Academy of Sciences. Okay, and this is Ecton processes at the cathode in a vacuum discharge. Now, what happened, as I understand it, is Mesiats went to America to present at this conference here. And there was a kind of, it was a bit weird because he says, I've discovered this new thing. In fact, he discovered it long before and done lots of things around it. But he was really laying it out to the international community at this point. And he was saying, well, you know, it's this, it can do all these things. This is how you generate it and so forth. At this I think it's this conference, or it might have been before, but certainly around this time, I believe in the early 1990s. Because it was after Ken Shoulders got his patents awarded. And so he was there, and I think it was Hal Fox. Hal Fox had bought the patent rights, I believe. I might be wrong in this, but I believe he'd bought the patent rights from Ken Shoulders. And he went up to, I think he was at the conference, and he said to Mesiats, he says, what you're describing are exotic vacuum objects or charge clusters. In fact, he preferred the term at the time, high density charge clusters, HDCCs. And he went up to Mesiats, he said, what you're describing is being well detailed in a book. It's in a selection of patents that have already been awarded in an international basis. And you know, it's great that you've confirmed it. And it was kind of like, oh, to Mesiats. So it was like, what do you mean you just confirmed it? It's like, you know how annoying that must be for someone who's spent so much and done such brilliant work. And it was kind of like, you're a bit late to the party, as it were. But it's good. So, no, Gordon O'Carty, this is not ectoplasm, this is ectons, and I will describe it. So I will go back to this, and I will try and make this a little bit bigger so that it's easy for you to see. Is that okay for everyone there? Is that okay for everyone? Oh, maybe I'll make it a little bit bigger. I'm going to be able to move around that. Okay, right. So, abstract. Explosive electron emission. Well, we've already seen some explosion today. Explosive electron emission from a metal, we've seen it from a metal, has been shown to involve not individual electrons, but electron bunches or avalanches. Electron bunches. Now, what do we know about electron bunches? Well, we've talked about electron bunches, haven't we? We talked about electron bunches because that, in 1992, is in the Solon patent as to what causes the coherence that leads to the two solitons of opposite magnetic charges that then cluster and cause a gravity-like decay, like a neutron star, and create other elements, the explosive events, which then lead to these coherent, synthesized crystals. Okay, so I've got here electron bunches. These lead to coherence, and this is also what is said in 2000 as a proposal from
Takaaki Matsumoto. And so electron bunches leads to coherence. Or avalanche is named Ecton. So explosive electron emission from a metal has been shown to involve not individual electrons but electron bunches or avalanches named Ectons. Ectons play a fundamental part in the cathode spots of vacuum arcs and sparks. Wherever there's a spark, there is an evo. Okay? Before an arc is formed, you must have a spark. Every time you have a spark, you have an evo. Ectons are exotic vacuum objects. They are initiated due to energy concentrations in cathode microvolumes. Energy concentrations in cathode microvolumes. You know what? I might have already said enough so that those that are out there following already know the whole point of this presentation. But let's see. Okay, so mathematical simulation of ectons has been performed using magnetohydrodynamics and similarity methods. Okay. Introduction. In general, an electron is emitted from a metal when it has received an additional energy from an external source and conditions for its tunneling have been created. The present review gives a description of the appearance of short-living electron avalanches or electron bunches. Electron bunches is that phrase again, such that electrons provide the conditions for their emission by themselves. This occurs through micro-explosions on the surface resulting from a high specific energy delivered to the metal and its strong overheating. We have named these charged particle avalanches ectons. The ecton is a constitutive process in explosive electron emission. Explosive electron emission, EEE. Important arguments for the existence of ectons are cathode craters. Oh, where have you seen cathode craters? Well, could it be in this 1980s book here called Arc Cathode Phenomena by Lafferty? And if you look at it, we'll show you some lovely images here of these kind of craters. What am I talking about? I'm talking about things like this. Can you see those? Can you see those? Look at that. It's even got a pretzel. It's got a pretzel there. Look. Pretzel. And more on this page. Like that. And more on... Well, there's more on there, but it's too small for you to see. Here, these are some classic kind of ones there. Like, you've got that one and those ones. Okay. Published in 1980 from work done, I think, at Bell Labs and stuff from 1932. Okay. Important arguments for the existence of ectons are cathode craters. You've seen a bunch of those. Sharp oscillations of the... what is it? Oh, God. Explosive electron emission, current density with a period of 10 to the minus 9 to 10 to the minus 8 seconds, discontinuity of the glow in the cathode spots of vacuum sparks, and arcs. When speaking of ectons and explosive electron emissions, we imply that the metal confined in a microvolume of the bulk material experiences just what takes place in an electrical explosion of a conductor. Just what takes place in an electrical explosion of a conductor, like Leonid Oryzhkov. And Leonid Oryzhkov discovered strange radiation, which are coherent matter traveling waves, via exploding conductors. And he wasn't the first to record it. Of course, I've shown you that in Ken Shoulder's 1986 book, EV, A Tale of Discovery, he actually had an EV track on that aluminium foil, I believe it was, which closely matches some of the ones that Dave has produced in his reactor, and also Henk. And he proved they were magnetic charges. So right here, at this point in this paper, we already have everything coming together quite nicely. It's very satisfying. It's really satisfying. What am I referring to? I'm referring to what I showed you just a moment ago, and I said, hold it in your mind. I'm talking about the Leonid Oryzhkov work here with these exploding foils, and they're producing these magnetic monopoles, which leads to strange, well, you get strange radiation. Ball lightning. This is ball lightning. You see how everything's coming together? Okay. All right, so let's kill that. Okay, so from the viewpoint of the that is exploding charge. What is it? It's EEC. It's down here. Electrical explosion of a conductor. From the viewpoint of an electrical explosion of a conductor, physics of most interest for us is the fast heating of an electrically exploded conductor at a rate of over 10 to the 12 kelvins per second. 10 to the 12 kelvins per second. That's a lot of quick heating. Okay. Okay, so a numerical simulation of an ecton. The cathode is heated within a time of the order of 10 to the minus 9 seconds to a temperature of several tens of thousands of degrees when thermal field emission occurs, with the current density above 10 to the 8 atoms. Okay, this time frame and this amount of atoms per centimeter squared is getting on to what Adamenko used to produce this. It's in the range, and he produced these structures that persisted on his accretion disks, which were then able to act essentially a bit like black holes. They were able to cause matter to be captured and to emit light with an exponential decay, and no matter was able to escape, and it was just this, what you might call Hawking radiation, that we're getting out. But they're not black holes, they're black donuts. Okay. Anyway, and so there we have it, and several tens of thousands of degrees. Well, if we have several tens of thousands of degrees, right, what does that mean? Well, that means that we're well over here. If we've got 1 tens of thousands of degrees, we've got like 75% of the matter. You can imagine over here of this is asymptoting towards 0.9. So maybe you never get to 100% of all matter, even at tens of thousands of degrees. But you could probably imagine you get to 90% of all of the electrons and all of the ions in a particular body of matter are participating in the production of the cold neutrinos, the neutrino and antineutrino pairs. What about this point E for E5 EV value? Well, let's go back. Okay. Nothing else of interest. I want to go into that page. Right. Okay. Now this, I'm going to have to zoom this down a bit because you actually have to see this. You kind of have to see this. Oh, it's just such a pleasure to be able to get this off my head. You have no idea how long I've wanted to go through this. Right. Okay, so figure 2 presents time dependencies. There you go, Corky. Time dependencies of the radius of emission zone, R0. So we have a point here. We have the radius of emission zone, this radius here, and the radius of the melt zone, this melt zone here. The emitter geometry is shown schematically. Okay, so this is like a spike, right? Now, what could this spike look like? Well, let's go back to our presentation here. And what do we see? This is 20 microns, this full scale here, okay, on Bob Higgins's SEM. One of these is 1/10 of that, so that's 2 microns. So that distance is 2 microns, okay? Half of that is 1 micron, so that's 1 micron. Like there to there is 1 micron. So you can imagine the tips of some of these structures, particularly over here, they're very, very sharp. You can imagine that these are 0.1 of a micron or 0.2 of a micron. Certainly I would suggest they could fall within that boundary at the tip. Yeah. What does this mean for what is being said by Messias here? Well, if you have a micrometer here, this is this radius naught here of this spike, and you have 0.17 of a micron, that is that's 170 nanometers, okay? I think that is quite in line with what you are seeing the structures at the tips of these dendritic structures on the nickel used by Alexander Parkhomov, okay? And what does that give you? Well, I'll just talk through the bit here, but we'll come to it.
The next step in the development of the mathematical model techniques was one fluid magnetohydrodynamic model. In explosion, the erosion products go through several phase states. A material with a density close to the solid state density, that's 10 to the 23 per centimeter cubed, I guess, with a density close to the solid state density and with a specific internal energy exceeding the binding energy, a mixture of a liquid and gaseous phases, and finally a state corresponding to a non-ideal plasma with a particle density of 10 to the 20 to 10 to the 22 centimeters cubed and lower. Therefore, for the conclusion of this method, we used that described all these stages of material transformation. Okay, so blah, 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 blah. Calculation sets with B equals 10 to the 10 amps per second, and the angle of taper, phi, or theta, or whatever it is, varied from 12 to 40 degrees, have shown, so this angle here is 12 to 40 degrees, so that's somewhere between here and here, that irrespective of the latter, the point tip explodes as early as at t to the 0.5 nanoseconds. Okay, the specific thermal energy is distributed non-uniformly in the exploded material and reaches 20 to 50 kilojoules per gram. Okay, now if we're at this area here and we have this temperature here of 12,000 degrees Kelvin, and we have joules here of 5.6 times 10 to the 9 amps per centimeter, that's pretty impressive, isn't it? So now, did I highlight it? Is it down here? Okay, so the plasma produced by the micro explosions contains, depending on the type of metal, singly, doubly, and even triply charged ions. These ions have a rather high energy. For instance, single charged ions have a velocity of 1.5 times 10 to the 6 centimeters per second, are accelerated to 70 electron volts. 70 electron volts, okay? What do we need, according to Alexander Parkhomov, to achieve the production of neutrino and antineutrino pairs? We need 0.5 electron volts. 0.5 electron volts. What does he claim they're observing through the calculations? 70 electron volts. And that, my dear friends, is for single charged ions. Not for doubly charged ions and even triply charged ions, but single charged ions. Now, I don't know whether it's higher or lower, but at least the singly charged ions will probably be those that are in most abundance. And that is 70 EV. That is a lot of energy. That is a lot of temperatures, actually. It's a lot. So there's going to be a lot of collisions, and as they collide, they are going to potentially create these cold neutrinos. Okay, the cathode surface condition and the initiation of an Ecton. Now this is really important. When you read this, I tell you, when you read this, it'll make you laugh, because it's like everything that everyone's ever been doing, it's like they read this paper. It's like they read this paper, or they reinvented the wheel because they didn't read it, sadly. Okay, so the initiation of an Ecton means that in a cathode microvolume of an energy has been concentrated necessary for the material confined within this microvolume to explode. This process strongly depends on the surface condition of the cathode. An important role is played by three types of surface imperfection: microprotrusions, adsorbed gases, and dielectric films and inclusions. The cathode surface has micro irregularities induced by various factors such as mechanical treatment and heating. Right, I'll give you something here. One, the carbonyl nickel obviously has the right kind of protrusions. Okay, it's all protrusions. Two, adsorbed gases. Well, on nickel you get hydrogen species adsorbed. You get hydrogen species adsorbed. And then Celani, on his Celani wires, that is the first work that the MFMP did in replicating something. He's provided the wires. Now, what did Celani do in his wires? Well, he joule heated them, so it produces these oxide structures, okay? And then as part of the process, I'm cutting out a whole bunch of steps. One of the things he did is he put sol gel on there. And what the sol gel does is after processing, it produces silicon dioxide. And what is silicon dioxide? Well, it is a dielectric film. He was putting dielectric films onto the copper nickel of the constantan wire. Literally achieving everything you need to create ectons, which are exotic vacuum objects. The absorption of gases or vapors by the surface of solid is named adsorption. This is what everyone's doing in LENR. From the chemical viewpoint, an adsorbent has on its surface atoms with, that's the thing doing the absorption, i.e. the nickel in our case, in Parkhomov's case, has on its surface atoms with an unsaturated valence. Particles in number sufficient to saturate all surface bonds form a monolayer. This is very, very important. Since the adsorbent particles in a monolayer are bound by chemical forces, this type of adsorption is referred to as chemisorption. A solid having on its surface a monolayer of atoms has no free valence. Therefore, new layers may be formed only under the action of polarizing van der Waals forces. This type of absorption is spoken of as physical absorption. In the case, desorption of atoms and molecules may occur even when the surface is heated by hundreds of degrees, but not maybe with the chemisorption. In the atmosphere of gas, in the atmosphere of a gas able to oxidize metals, the cathode surface appears to be covered with an oxide layer. Moreover, contaminants and dielectric inclusions may be left on the surface after polishing. The simplest way to initiate ectons is to cause an explosion of the cathode microprotrusions, or specially prepared points under an action of a field emission current. And this is essentially what Mizuno used in some of his experiments. He would actually do discharges and cause pre-treatment of his material that he wanted to do some adsorption and become active material. So literally in these few sentences you have so much detail of what everyone's been doing in LENR for a very long time, and this is from 1996. Okay. And by the way, these are all the things you do to create ectons, and ectons are exotic vacuum objects. Okay, for a liquid metal, or they lead to also exotic vacuum objects. For a liquid metal cathode, the surface structure is destroyed under the action of electrostatic forces. As the electric fields exceed some limiting value, a hump starts growing on the liquid metal surface. The electric field at this hump increases, which leads to further stretching of the liquid at this site. And so you've got an image here, and you've got some liquefaction of the surface, and then you've got some field that's causing this thing to grow up here. I've got an itchy nose. Growth of a microprotrusion on a mercury surface at the different electric fields. Now, mercury is used, or liquid electrodes are used by some people in this field, but mercury was first used in electrical devices, switching devices, but in something that was producing microparticles of electrical matter, or electrical particles of matter. It was used in the 1930s drawings of Tesla's death ray. So he used mercury there, or tungsten. Anyway, so the growth of microprotrusions on a mercury surface at different electric fields between the electrodes. The field in this case is higher than in case B. Okay, so initially, the hump has roughly the shape of a spherical segment. It then transforms into a cone, which can explode under the action of field emission current. This is like a Taylor cone. Okay, the formation of microprotrusions as a result of melting of a metal in an electric field is confirmed experimentally. On a metallic surface, there are dielectric films of varied thickness. This film strongly influences the tunneling of electrons from the metal. This shows up as an increase in electric field enhancement factor, BE. The breakdown of thick dielectric films in their
charging with ions plays an important role in the initiation of ectons. As the electric field at the film becomes high, the latter is broken down. The breakdown current just initiates an ecton. A commonly used way to initiate an ecton is to induce a vacuum discharge over dielectric being in contact with a metal. This is hilarious because this is exactly what Ken Shoulders does in his patent, which is I think awarded in 1988 or 1989. So it must have been so annoying for Messias when he presented this. The metal dielectric vacuum contact point is named as a triple point. It can be produced in vacuum on the tip of a metallic needle, resulting against a dielectric plate. This is literally the diagram. If I was to go and show you, it's literally the diagram from the Shoulders patent. Let the backside of the latter be metallized, okay? So he's got it here, he's got a graph and how it occurs. When a pulsed voltage is applied to the trigger electrode, a surface discharge over the dielectric starts operating from electrode 1 in the diagram, electrode 1 or whatever. The current of the discharge will be closed into the cathode micropoint resting blah 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 blah. When the current is high enough, the micropoint explodes and the ecton appears at the emitter. Electrical explosions current will then flow towards plane anode 3. The current of the surface discharge over the dielectric is due to the increase in the dynamic capacitance between the discharge plasma and the metallic layer deposited on the dielectric. This is highly efficient and simple technique for initiation of ectons. It is utilized in various types of vacuum spark gaps and metal dielectric cathodes. He's literally saying that spark gaps and metal dielectric cathodes have been using this for a period of time, right? He's just explaining what's going on. This is not new. It wasn't even new when I believe Ken Shoulders was specifying what actually is going on. It must have been, I can't imagine how annoying it must have been. And this is, if you think you have discovered something, you're going to get it out into the public somehow, some way. Because you don't want to be the guy that said, oh yeah, I invented that. And it's like, no, you didn't. They did because they said it first. They might have actually invented it 20 years before you. That's just when they delayed it too. You know, if you think you've got something new, you've got to get it out, right? Otherwise, you're just an also-ran. Okay? And it's just annoying being an also-ran. Okay, so this is about where I got to in the reading. So I think what I'll do is I'll just skim read some things and maybe pull some other stuff out. But I think probably you've got the basics of this, that what's going on is, if we look at with what we've already read so far in this paper, we have, if I go here, we have already shown that structures of the form are idealized to produce ectons, and that these will store themselves in metals. Okay? Now, I've already described at the beginning of this presentation one metal which is highly good at doing Lena, and that is tungsten. And what was Alexander Parkhomov using to heat his reactor with? He was using a tungsten filament for doing the heating. And so we already know that these structures can pass through, from the work of the Dubna City for over 9 years of research, leading to string vortex soliton characterization, which are the neutral form of exotic vacuum objects, and they call them magnetotoroelectrical radiation, but they give credit to Shoulders. And they've been shown by Roitskiev, and coming out of reactors, and we've seen them too in various different systems. So, and in fact, actually, another example of where these things are active long after is what I experienced as my first strange radiation tracks, was the emissions coming from the ultrasonically produced Suhas Ralkar Echo fuel. That was coming out months and months later, and observable on various different detection methods. And so this is able to travel over a distance. And actually, if you go to ICCF 23's paper, Alexander Parkhomov reiterates again that he found different elements in different parts of the reactor, showing that the things had been moved around. And I've shown this in the Lion reactor, where
you've got spheres of things that have teleported themselves into and out of the quartz, and all over the reactor. Just they're coming out. And so this is explained by these things that are able to encapsulate matter and effectively teleport them through other dense matter. And this again in that 2010 transcript between John Hutchison and Ken Shoulders, you can see that he's explicitly talking about this and walks through why that's occurring. So I believe what is going on in Parkhomov's reactor is that the nickel, when it's in this state, as you are heating it up, is adsorbing the hydrogen. That is forming a layer on the surface, which produces an ideal scenario to produce ectons. Okay, because you have the right formation of structure and you have the adsorbed layer of hydrogen. And then you get it to a point where there is the energy concentration on the peaks. This produces the explosive electric emission, and these have, even on the singly ionized, 70 eV and tens of thousands of degrees and kinetics. And because it's coming from a point, just as we know Ken Shoulders uses a point, and just as we know 1930s death ray used a point, or in the form of a tungsten wire, or in the form of a Taylor cone from mercury, you will get these electrical particles of matter, as Tesla called them, which are exotic vacuum objects. And they would produce these solitons coming out. They will plasma pinch down, and the temperatures are everything there with the density of matter to produce the cold neutrinos. And therefore, you get these things that are able to go through and interact with silicon carbide, fusing silicon and carbon to isotopes of calcium and further out to the tungsten, and causing material to disrupt in ways that are not natural, because when they get loaded and loaded and loaded with these things that form into pseudomagnetic monopoles, they can cause disruption of matter in novel ways. Okay, so let me just have a skim read through this, and then there's two presentations. One I want to talk about from some national labs, which are a little bit further down the line in terms of looking at this, but basically ignoring the works of Shoulders again, and basically ignoring the work of Messier again. And so it's just like, I don't know how these guys get by getting into their positions and having these big budgets and just ignore the primary research on it, where a lot of it's already done and well characterized. Anyway, I've really got an itchy nose. I don't know why I've got an itchy nose. It's quite sore. I was in the garden. Maybe it's in sun. Right. The criterion for the appearance of... Okay, it's getting warm in here as well. So if the camera goes off, I've got my backup camera. Are there any questions at this stage? So Chris Adams, you're going to see tritons when you have a thin film, and if you've got field emission and you've got corona discharge. I was standing next to with it was a great honor, Tom Claytor from formerly from Los Alamos National Laboratory, who proved that using corona discharge, what light was done, I think, in the 1930s. I can't remember his name. Very famous British, Scottish, probably British researcher. Why can't I remember his name? Anyway, it was first observed by him and then by Correa, Correa researchers. But he proved that you could produce tritium in this way, and I believe that in the corona discharge, when it gets to a level of stability, you are forming coherent matter. The coherent matter forms clusters. The clusters then go on to, and also you get ectons produced, and the combination of these will lead to some fusion, and some of these things blow up and they emit a certain amount of like byproducts, which tritium is kind of like a leftover, even if it's actually forming. So the tritium's already been done. It's not a new discovery. It's been known for a long time. And Tom Claytor got the award, I think, in it was in ASTI in 2016, I think, June the 5th. Was it? Anyway. Yeah, it might be Rutherford, Gordon. Anyway, I've talked about it in the past, so that was done a long time ago. But really, a lot of this you can send back to Langmuir. Okay. Yeah, when you, it's not quite the same with Papp's. It certainly is. Papp's device is much closer to the 1973 patents on what do they call them, Plasmax. And I've talked about that. You can go and have a look at that. It's all it's free to use now. When you really understand the Plasmac work, you understand Papp, and they're kind of like contemporary. I think probably Papp was not favoured because, you know, the other work already was contemporary. The protrusion is a fractal of Wardenclyffe. Well, you kind of like have no idea, do you? It's kind of exactly it, really, on many scales. When we read on and we look at some other things, I think you'll find that's quite funny. Explain non-ideal plasma. I don't know, actually, to be honest, but a plasma technically should be ions and electrons. If you have Rydberg atoms where they're called ion-electron pairs in other phraseology, they are where the electron is far dissociated from the atom, but it's not actually separate from it, and it has an elliptical orbit, and they have different levels of which they can have this extreme level of elliptical orbit, and they become polar, actually. So I think an ideal plasma, I'm just guessing on riffing, I imagine it would be neutral, whereas there would be different species in a non-ideal plasma, which would include ion-electron pairs. It's now getting really hot in here, so I expect the camera will drop out, so really hot. Talking about double layers, I'll just go back to this presentation, and you will know from our Vega experiments that we had this situation where the coherence got to a certain level, and it instantaneously ate the wire, and it kind of makes me think something similar to what you're seeing here, and where there's this zone here, which is the emission and evaporation zone. This is where the ectons are emitted from, and we have this liquid phase, and it almost looks like you could imagine a ball lightning forming on the outside on this actual point here. Anyway, we'll hold that for later presentation, part of this presentation. Okay. Yeah, so 85,000 degrees compared to 70 electron volts. Go and look at what that means in temperatures. It's a lot of temperatures. 85,000 degrees is like just scratching at the surface. It's like, yeah.
Anyway, it doesn't matter. You only need tens of thousands of degrees. In fact, you only need to be over 1,000 degrees and be in dense matter. This fulfills the requirements to produce what is observed by multiple parties, which can then go on, do the transmutation and then the weird effects that we've been talking about. Where does the energy come from, Axel? It's self-reinforcing energy concentration. I will show you many more slides from a presentation that was given in 2013, I think, by Messiatz, and also by something, I think, 2015 later. I just want to see if I can pull out anything other useful from this paper. There's many, from my recollection in the past, when I read it over a year ago, there's some other important stuff. I just didn't get time to read it today and highlight it. Okay, so just see if we've got anything down the bottom. You don't need platinum or palladium in this work. This work is, I mean, Alexander Parkhomov's reactor is the longest running excess heat generating device that has any level of independent study gone on it. And in fact, I think he gave us samples without any requirements of whether we to publish, what we could publish, how we could analyze it. And we found, well, one thing we found is this beautiful pretzel in it, the absolutely stunning proof, in my opinion, of magnetohydrodynamics at work. And it had the elements you would expect in the parts of the structure. But also that we found lead in there, actually quite large lumps of lead, but it's not like a blob of melted lead. It's a lead that has this structures in it. It's just beautiful, and obviously calcium in there and other things. So okay. Like I say, people don't really have to reinvent the wheel. Between this and shoulders, you kind of have everything you need. You just have to bother to read it. I mean, that's the biggest problem, I think, is people like to go, oh, I've got a brilliant idea and I'm going to reinvent the wheel. And 20 years later, they find out they've just done what was done in the 60s and 70s or 80s. There's a lot of really, really hard-working people that sat down doing experiments. And it can't be, it cannot be a coincidence that both Shoulders and Messiatz came up with basically the exact same thing for the same reasons. And one put it into a pattern just before the other one talked about it. Okay. Right, so I need to zoom down from this, and I'm just going to look through this. So, change my mouse. La da da. Okay. These are different shapes. Schematic of cathode protrusion. So the group at Tohoku University are trying to create this kind of structure, and this creates a occlusion in their patent. And the interesting thing is that this is the same kind of structure and the same terminology that was used, I think, in 1876 by Thomas Graham, FRS, who was the person that defined the maximum amount any element could adsorb or absorb isotopes of hydrogen, and he proved the palladium ratio. So there we go. So this is their kind of idealized shape, but this is the kind of shape that you get a lot of on the Parkhomov 225-day PNK02 reactor. It's essentially exactly what you need to produce ectons, which are microball lightning, which are itonic clusters, which are your evos. So, you know. Okay, so I think what I'm going to do is I'm going to go to the later presentations. I mean, there is some really important information in here, and it would be nice to discuss it in another thing. You know, here talking about laser radiation, focus on the cathode surface to a spot of diameter of several millimeters. Plasma is observed to appear in the radiation energy flux state. This energy is too blah blah blah. We'll actually look at images of where that occurs. They've got different materials here. So here you've got like the crater. Now, this is essentially what is discussed by one of the presenters at ICCF 23 just over a week ago. And he's talking about it forming a shape charge and blowing out and making a crater, and there's nothing special about it, and it's just Coulombic explosion. Yes, it's Coulombic explosion, but it is special because it is fulfilling all of the requirements to create the things that have been observed by many parties. And so you get these craters. So you get a melt zone, it comes up, forms a Taylor cone, and then you get an explosion of that, and it forms the crater. Okay, so let's have a look to see if there's anything new in the conclusion. Thus, we have shown that rapid concentration of energy in the cathode microvolumes to high density of W is 10 to the 4 joules per gram results in microexplosions accompanied by explosive electron emission. This emission occurs in discrete portions of electrons, ectons. The mass lost by the cathode is removed by portions as well. This discreteness is due to the fast cooling of the emission zone after microexplosion that occurs through heat conduction. A decrease in current density and reduction in the mass of the heated metal and plasma ejected from the cathode. Blah blah blah. In the author's opinion, the Ecton theory may serve as a key instrument for unbridling the mysterious nature of the cathode spots of vacuum arcs and sparks. As said in 1996. Right? Okay. All right. Let's go and have a look at some other presentations. One by Messiats in 2013 and one by other authors. So this is the first one. It's quite nice because it's got some more pictures and you can kind of get a better idea of what's going on. You see kind of like how advanced their thinking's gone. Okay, so I think maybe if I'm doing this, we might actually get some translation going on there. No, I don't know. Okay. Okay, I'm gonna make it translate into a different language. Why not? Give me a second. I think is there a particular language people want? I think I'm going to put up Italian. Why not? Let's put Italian up there. Italian. I should probably put up Russian, but anyway, we'll put Italian. Okay, for a bit of fun. Okay, play from start. Okay, so now it might be actually getting my language correctly, and there we have the Italian. So for those that are interested in seeing this in Italy, we've got a lot of friends in Italy. If I put my mugshot up there, you won't be able to see it. So I'm going to kill that. Okay. All right, so this is the presentation, initiation of explosive electron emission pulses, ectons, as initiation of vacuum discharge stages. The breakdown, the spark, and the arc. So we know when we have a spark, we have exotic vacuum objects formed. This is the central claim of Ken Shoulders, and therefore this is the same kind of thing. So you can see this kind of structure here, which looks very much like the kind of structure we observed on some of the Vega Valley. However, the interesting thing about the Vega Valley is that it's not a simple arc discharge. It is, I believe, coherent matter that's traveling around, and it's its own plasma and self-supporting. But in the course of this presentation, I think you will realize that
something that might explain the kind of wildfire of John Hutchison and it being similar to what is being shown on this. So let me go ahead. And so here is the kind of the sort of diagram here of what we were just showing in the paper from 96. Okay, so the outline: vacuum discharge phenomenology, explosive electron emission properties, explosive emission initiation at a clean and contaminated film-like surface, and resume. So there's your charge differential. There you've got some vacuum breakdown, and in fact, vacuum breakdown actually requires some kind of emissions anyway, and so forth. Vacuum spark initiates, and then the arc is a continuous flow through the spark. This is where the interesting business occurs in the form of exotic vacuum objects. Okay, and you'll have seen all of these things in the Vega experiments, all of them. So here's some kind of like much more detailed sort of images showing the process, and it's detailed the kind of time that it takes to go through here. And I think, well, I don't know, is that in milliseconds, microseconds? I don't know. But they've got all the timings there. So that answers the questions that people were having there. Typical photos of the luminescence in a vacuum gap taken at different stages of breakdown. Common electron emission: thermo, field, photo, and secondary. Remember these terms. We will come back to them. We will come back to these in future presentations. Nudge, nudge, wink, wink. Go and look them up. What do they mean? What can you do with them? Vaporization: explosive electron emission, boiling, non-stationary local character. So explosive electron emission, EE's pulse from the explosive center produces the electron bunch. Electron bunching leads to coherence. When you get coherence, you get ball lightning, blah, blah, blah. There is a positive feedback for the dual NG release leads to the explosion. This is what I'm talking about, Axel. This is, you get a positive feedback. One pulls the other forward, pulls the concentration, and gets this dual NG release to the point of explosion, leading to the Ecton release. E-ignition due to needle electrical explosion, dielectric film breakdown, triple point, microparticle impact, plasma and particle flux, energy flux, laser. So remember what Lowe said. If we wanted to create basers, we can use a laser to stimulate the production of basers. And they're using a laser, and they create something which is producing electron bunching, and electron bunching being electrons, and if they become coherent, are matter, and they are coherent matter, and therefore you are getting the electrons forming Cooper pairs, and the Cooper pairs are bosons, and as they are coherent bosons, they are in a thing, and if they form a wave, that's a baser. Okay, there we go. General requirement: energy concentration 10 kilojoules per gram in microvolumes at the surface. Okay, explosive electron emissions issues: pulsed power generators of E-beams, X-rays, microwaves, a considerable advance in the development of nanosecond and picosecond pulse power supplies. And so they actually have some things that they've invented with this knowledge. And this book you can go and buy. Actually, I should buy it. I think it's a very valuable book for people that are interested in this field. Physical mechanisms of the vacuum discharge, the breakdown at the spark and the arc, and so forth. And they've got the papers down here. Okay, so here's an example. This is a kind of like, look what this looks like. This kind of looks like our ball of lightning sitting on our spike, doesn't it? It looks very much like what we've seen in the Vega experiments, but on the anode. But you get these things in other circumstances as well. And so they've got the equations. But here are some examples of the sort of things that you will see. Right. A, dielectric inclusions. Okay. Sorry, A is micro protrusions. A spike, okay? Dielectric inclusions, like this is a piece of quartz and it's stuck on our piece of metal, okay? This will lead to the production of ectons. Oxide and other or inorganic dielectric films. So if we would take our palladium dust, our palladium powder, and we were to compress it so that there was a lot of density there, but there was still open volumes for the gas to get in and able to oxidize it, you would have a beautiful scenario for creating ectons, wouldn't you? Well, This is exactly what Ed Storms has proposed, produces Lena excess heat 100% of the time at ICCF 23. But right here in 2013, it's spelt out for you in a recollection of historical claims from 1996 by Messiatz et al. Okay, so this is D rather, is what? Adsorbed gas layers. What are absorbed gas layers? They are hydrogen on the surface of nickel. This leads to the production of ectons. This leads to the production of what? It leads to the production of exotic vacuum objects. B. Where are we? Sorry, this is not E, it's E. I'll get it right in a minute. Grain boundaries emerged at the surface. So we have little cracks or grain boundaries here. They can form a focal point for the production of ectons. C. Sorry, God, I'm going to... At one point I'm going to get this right. Microparticles. We've got microparticles on the surface of something else. This is what is being produced when you discharge onto something in the Mizuno previous series of work that he was doing. Mizuno was learning from Messiatz or not bothering to look at Messiatz. But this is essentially what was being done by Piantelli. Piantelli had a $1 million device that was custom built, and he was producing microparticles on the surface of his nickel by splat cooling from vapor. And so essentially you can have a scenario where your reactor produces a plasma, produces microparticles or microcrystals, and the microcrystals then go on to produce better ecton surfaces, right? You can imagine that what I showed you from the titanium perfect dendritic crystals, they would actually be really good ecton emitters. So you can see that the process itself could lead to the production of things that are good for producing exotic vacuum objects. But once you've got them and they are in metals, you can get them to do work by stimulating them by phonons or bosons or whatever you like. Whatever you like. G is oil vapor cracking products. Okay, and this has been observed. There was a problem, I think, actually in Norway, where they would have these cracking devices in their oil production systems, and they would get these massive excess heat bursts, and they didn't know why it was. Well, if they had happened to read Messiatz's work, they would have known it was producing exotic vacuum objects. Ectons, and they would have known that that's what's causing it. H is edges of craters formed upon breakdown. So the little pointy bits you get here from a arc actually go on to stimulate the production of exotic vacuum objects. So this is probably why the Vega Valley was so good at producing exotic vacuum objects. So we already know that in the Vega Valley, we started with a crack, didn't we? We started with a crack, and it says pores and cracks. Now, Ed Storms has always gone on about cracks. Well, there it is. It's been there from the beginning in Messiatz's work. Okay? So they've got a description here, sphere on the tip. So this is the structure done by the Tohoku University, which I believe has its heritage in the work of the 1870s work of Thomas Graham FRS. This is an ellipsoid, so you can see one is more preferential over the other. But this is basically a Wardenclyffe tower. The sphere is one representation of minimum energy surface, but the toroid is the other, and the toroid has advantages as well. So electric field strength enhancement. So this is about enhancing the strength and stuff, and conduction bands and valence bands and so on, and this is all important. So you have some more detail here. Like I say, I'll make links to these presentations, but you can see this field. Now, this is almost like a pyramid, isn't it? Well, if you have a pyramid, you will actually have a different charge at the top and the bottom. And this will actually influence the environment around it. But here we go. We've got the charge moving up, the heating that causes excitation, thermionic emission. That leads to more acceleration of the process, and then you get the Coulombic explosion, and the Coulombic explosion is what can lead to the production of exotic vacuum objects and their neutral counterparts, which are condensed cold neutrinos. And I've explained why, and the energy produced by it, calculated and theoretically observed, leads to the production as observed. Okay, explosive electron emission. So I said I wouldn't do this without any equations, but if you want the equations, they're all there. Here's another image, and you can see the kind of like hot spots here in a kind of emission, the plasma density at these points. And here's a typical track, and this is the direction of progress of this cathode spot. And this is why I would like to get, and hopefully on Wednesday I will get the Vega Valley, the whole thing under an SEM, and I will look specifically at those tracks in the Eastern Plateau to see if they follow this line, or as we've already shown with some of the 3D projections, and one of the ones that I've shown you actually see these toroidal features and multiple toroidal features in there, which is much more interesting, and it much more fits something that is coherent and much more stable, as observed by Bogdanovich et al. Running for many days after exposure. So here we see this thing again, and we have the emission zone, and there's all the data. But you can see the heritage of this. This is in 2013. He presented the summary of how to do this in 1996. So I kind of explained this. Here we go. The Ecton charge at 10 to the 11 electrons. That's a lot of electrons, isn't it? But it's not as much as Ken Shoulders, I think. But anyway, 20 to 200 megawatts per centimeter squared. That's a lot of megawatts. Thermofield emission, 2D thermal balance, heating by instant plasma. So, okay, there's so much in this presentation. I'm just going to skip. But I think probably I've said enough to explain Parkhomov's observations, and also Andrea Rossi's Andrea Rossi's original nickel powder sort of thermocore type reactors. Actually, Piantelli did nickel powder. He told me, or he told us when we were with him in 2015. He said that, but they just did thermal runaway. They just melted down and sintered. So, which is the same as the thing that was observed by Thermocore. Okay. Okay. So there's a lot of equations. Blah, blah, blah. Intense energy flux, 10 to the 7 to 10 to the 9 watts per centimeter squared. Here's some pits. You can see some hexagon pits in here. So there we go. One hexagon. There we go. Dum, 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 dum. Initiation of arcing in tokamaks by dust particle impact. There you go, because the dust particle hits the wall, it produces an energy concentration, then because you've got the field of the plasma, that produces an ecton and so on. And then as the ecton comes out, it can form a plasma channel and itself cause a discharge to the wall. Okay, so he's got some different arcs here. This is sort of kind of similar, but these are kind of like traveling arcs. I think we're seeing more interesting things in the Vega experiment, and because we're not directly exposing the cathode to the anode, the cathode is comprised of stacked, in that case, brass plates, and there's a gap between where the main channel is producing the ball lightning, and there's some bleed out. And I was actually toying with how to explain that today, but I realized I couldn't explain it fully without going into the work of Messier, so that's why I'm doing that today. Okay, so here's the kind of event that you see here. Tandberg 1930 has found the particles flux of absent tens of eV. 1960 have found them to be the plasma flux, blah blah blah. 10 to the 20 kilometers per, that should be, I think, second, maybe? No. This might be a mistranslation from Russian, I don't know. Kilometers per centimeter, I don't think that's right. Okay. There's a protrusion. Is it Cockcroft Walton? Or is it? Well, anyway, it's a voltage multiplier, I guess. And he's doing a discharge here, and he shows these things. La la la, here's a discharge. These are the spikes. As it's traveling across the surface, you get the spikes, I guess. And he talks about the motion here. Role of easily eroding microstructure. This is in a tokamak, I think. And you get here, this is the anode. You get some plasma forming. This is the plasma, I guess, in the tokamak. The current circulates between the external plasma and the wall. Yeah, this is unipolar arcs, which is the big problem in tokamaks. And so you see this structure here with this dendritic kind of nature to it. This is very similar to what we observe on the Vega experiments. But like I say, it's not directly exposed to the anode, the main anode. There is little information on unipolar arcs. Cathode processes are the same as a vacuum arc. There are no reliable experimental data on discharge conditions. Okay, so there's a toroidal structure. Oh, so this is what you have. This is tungsten, and this is tungsten fuzz on the shielding of a tokamak. And they show how it can burn through the fuzz in tokamaks, and you get these traces. And in this case, they initiated the unipolar arc by hitting this area with a laser, and we know from the low work that that will lead to coherence. And so are we seeing a structure which is like ball lightning traveling off and doing its damnedest to eat the tungsten fuzz? But obviously the tungsten fuzz itself has these points which allow for energy concentration. This is one way that the plasma is described, and I think it's a good explanation, and it would also explain the wildfire when you get a coherent matter structure forming a plasma, and then you get this field emission from here. The field emission builds up concentration, and then you get an Ecton explosion, and the Ecton explosion then moves the plasma over to a new area, and then you get a new field emission because this is the bit that's prone, and so on. So this is how you can end up with these kind of these arc trails. And you can see here how it's come to a boundary, and it's bent round and changed direction. So this is actually more tokamak research. I think they've got these lithium coated walls, and the lithium is when I saw this, it was just hilarious because it's a liquid electrode. So you coat the wall with lithium. Now lithium, in one respect, is good for capturing the fast neutrons from the fusion reactor and actually converting those to tritons. So I think, yeah, you do something like that and you end up by producing tritium, and that actually feeds the reactor. So that's one thing. But the liquid lithium ends up by being a means by which you can self-heal the walls of the tokamak. So you can go and find that out. And there's a suggestion here in 2013 to use gallium as well in a cathode. So, like I say, most of the work that you will see in the field of LENR is really being talked about in the work of Messiat's for a long time. So you've got the pulses here for the various stages. It's very detailed, this. And this is this is a representation of the tungsten fuzz. And here you can see the tungsten fuzz has these nodules, which are in a way very similar to the spikes, the dendritic spikes on the PNKO2 nickel, carbonyl nickel, that is nickel carbonyl, no, carbonyl nickel, I'm going to get wrong, carbonyl nickel, that produces the 225-day reactor. So you get these field concentrations. La-di-da-di-da, da-di-da-di-da, lots of those talking about it. And here are the two different modes, and they discuss the two different modes, and that's about it. So I think you can, and it's saying basically this explains all the observations, and I think they're pretty much correct about that. Okay, so any questions at this stage? How much does water pressure matter for transmutation? Any work you could refer me to on that, please? Please ask the questions on that in the relevant remoteview.icu thing. I can answer those in more detail there. Yeah, the CRT is. People knows it was producing different radiation. And in fact, in the back of a CRT, often you would have in the old ones like a valve, and that would produce X-rays. It had like a warning on there, but you know it was shielded and stuff. Any biscuits? Biscuits would be nice, wouldn't it? Great, great on fixing Fukushima. I've got probably another update. I'm going to be traveling from Thursday, so things might be a very different schedule. I can tell you, it's with this cold that's been going about and the nonsense, especially for people that are immune like myself and my family. It's ridiculous to be having to pay really huge amounts for the flight and then double the amounts for proving that we haven't got something that we can't get and transmit or capture or whatever. It's tyranny of the highest degree. The other thing we found is that in the UK that no one is travelling abroad because of this tyranny and all the expense, and so all the accommodation in the UK is like stupid expensive. So if anyone wants to host 4 people after the 5th of July for a day or thereabouts, let me know. Did someone lose sound? Is it clipping? Are we losing sound? I don't know. Oh. Sorry if you lost sound. I am recording it locally if there's a problem. Corky, question. Are you familiar, Bob, with steradian related to spheres and measurement? Maybe not with the term. Okay, so I'm just going to quickly run into this other presentation. Oh, sorry, Agent X. Yeah, okay. Sorry, I can't position that Italian. I guess I can put it down the bottom. Let me just fix that. Although, yeah, in the next presentation, which is also a PowerPoint, I will drop the Italian to the bottom. Sorry, I'm trying to get better at this. I managed to get the camera to not switch off, but I think it's probably going to switch off in a second because of the temperature in here is just getting unbearable, and I'm not going to take my shirt off. Dear. Right, where are we? This one. I want which one? This one. This one. Yes. Right. So the previous one was from 2013. This one is from a different time. Okay, I will kill the other presentation because that's running my computer too slow. Okay. Right. Now, slideshow, subtitle settings, below slide. Ooh, no, below slide. There we go. All right, let's do this. Let's do this thing. Okay, so this is from Argonne National Laboratories, and it's sponsored by the U.S. Department of Energy, University of Chicago Office of Science, and it's a U.S. Department of Energy laboratory managed by the University of Chicago. And it's from the muon cooling RF workshop. Atomistic mechanisms of RF breakdown in high gradient linear accelerators. Okay. Unipolar arc plasma models in various systems, plasma surface interactions, plasma model development by MD, self-sputtering of copper surface, Taylor cone formation. There we go, we got Taylor cone formation, Coulomb explosion. The Coulomb explosion, there we go. Summary. Okay, so we have a hotspot. How does that occur? Don't know. We've completely detailed it with the work of Messiat's. We have a Taylor cone forming, and this forms what? What does this form? Heating occurs via ion bombardment, plasma fueling, evaporation of surface atoms, tip explosion by high electric field. Why can't you mention Messiat's? Why can't you? Why can't you do that? Why? Unipolar arc model in tokamaks. And so we got some things coming up here. The positive comes down. These are coming down. The E field comes down here, and so on. Typical parameters for self-sustained, self-sputtering, superdense glow discharge in pseudospark, hollow molybdenum cathode filled with H2. Heating occurs via ion bombardment, plasma fueling, evaporation of surface atoms, tip explosion by high electric field. RF breakdown on copper surface. Heating via ion bombardment, plasma fueling, evaporation of surface atoms, tip explosion by high electric field. There we go. Sputtered neutrals. So these are the neutral atoms. They're not ionized. So on. Blah, 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 blah. Have a nice direct image here. Firstly, you get shock waves going through the material when this thing explodes. But you also get cluster emission. Cluster emission. Why can't they call it Ecton emission or evo emissions? I don't know. But anyway, that's what they say. La-di-da-di-da, not so interested. So this is kind of like a cycle that you could get. And you can imagine this going on inside the Vega Valley that is causing deposition and going on. But there's more going on in the Vega Valley. And when I talk through that, I think you will agree there's more going on with that. Okay, sputtering yield modes. Not so interested in that. Not so interested in that. Equations, you don't like that. Okay, so they've done some 3D modeling here, or some computer modeling on the formation of Taylor cones and energy concentrations. But effectively what this is doing is it's creating a nanoparticle. It's creating structures that are suitable for the production of ectons or exotic vacuum objects on the fly and so on. I will tell you now that by accident I was invited to see a Zoom call, and the guy was a very, very senior lifelong researcher and probably Russia's foremost expert in field emission. And in fact, during his presentation, he showed a photo of him at an American conference standing next to, or one apart from, Ken Shoulders. I actually think I have that picture somewhere, and maybe I'll drop it into the Remote View blog after this. But he actually showed in his presentation carbon turning to a liquid on the surface and forming cones. I'll just let you think about that for a minute. Carbon sublimes. Why would it be doing that? Anyway, so there we go. So that's it, forming Taylor cones, blah, blah, blah. And are we going to learn anything more from this presentation? Not really. Results, Monte Carlo, la 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 la. Like I say, I'll give a link to a copy of this. So here's this is actually an experiment Taylor from 1964 of the cone. You've got this kind of like glow here, then you've got the cone forming, and then you have these are the atoms in the 3D model, and this is forming the cone and the spike and the explosion emission. And here's the field, so forth, from this. And if you can imagine the surface of the electrodes, the large copper electrodes in the sapphire reactor, you can imagine this kind of thing going on, can't you? but in very localized areas. Anyway, there you go. Energies of exploded atoms. And in their case, they are observing some energies up to 0.18 V. Here we go. Look, here we go. Some of the energies of these atoms are 0.5 EV in their calculation, in their scenario, with whatever they were doing. And 0.5 EV is enough to create 2 cold neutrinos. A unipolar arc plasma model is used to understand self-sustained and self-sputtered plasma formation and RF high gradient breakdown. An MD model was developed and self-sputtering yields of copper ions were calculated for a wide range of ion energies and surface temperatures and compared to experiment and other models. Sputtering yield was calculated for solid and liquid surfaces for T300 to 1300 Kelvin and energy of 50 to 150 electron volts, typical for unipolar arc. Okay, so this is in line with what is observed in that paper from 1996 by our friend Messietz. And if we see here 1300 Kelvin, well, the reactor of Parkhomov was running a lot higher than that, but of course nickel like that starts to sinter at about 450 degrees. So even at the low end, at 300 degrees before the sintering temperature, you've got 50 EV there. So that's pretty cool, if I'm reading that right. Coulomb explosion mechanisms were simulated, and the energies of copper atoms were calculated. A Taylor cone formation in the high electric field was simulated for the first time. The simulated apex angle of 104.3 degrees is close to the experimental value of 98.6 degrees. So there's the cone angle, and you can do your calculations based on that. And it would be interesting to try and calculate from the SEM images that we have shared already of the Parkhomov nickel, what the actual cone angle must be, assuming a point in the center. And I'll just go back to that. We are close to understanding of the whole plasma surface interaction in RF Linux, and we it's like close. I think you were already told a long time ago. Anyway, I guess they can get another grant. Call me a cynic. So let me go back to that slide. Yeah. It's going to do it. Oh, my machine's really struggling now. Okay. So the question I started with today is, how could Parkhomov's 225-day reactor get started? And I believe the answer to the question, as I had it in my head in September 2019 at ICCF 22, when I was asked that question, I kind of had this in the back of my head, and I'm thinking, I'd love to have a long form here to just be able to run through this, but anyway, I'll get to it at some point. And here we are getting to it. And keep running even after the nickel had melted. This was the question that I got asked over and over again. How on earth was this producing energy if the nickel's just one big blob? It's because it doesn't matter. It does not matter. This produces the structures. They get caught in the metals here, and in the metals, in maybe the silicon, whatever, and in the metals of the tungsten, of the heater coil. And that goes and produces the energy. Because what we know is if there's calcium in here, not only if it was silicon carbide, you have those fusing to produce calcium. We also know from a Marsa gas that coherent matter structures interacting with tungsten produced from a Marsa gas produce calcium in every single area we sampled. Every single area. And why? Because if you look at the most likely fission product of tungsten, it's calcium and xenon isotopes. And so from the actual material that the silicon carbide that the core was made from, and I don't think this is a picture of the actual core. I think this is deliberately not that, but I forced the answer from him by asking about the carbon before the presentation. He kind of had to tell me. And the outside tungsten, you have two modes in which you would most likely get calcium produced, which would explain the observations. Okay, and The Papp accident, I believe, was Coulombic explosion, and it was Feynman's own account that I can tell you, it was Feynman's own account in context with what I understood about Papp and Adamenko and what I'd seen with Suhas Ralkar led me to believe it was a Coulombic explosion. That led me down that Coulombic explosion route. And then the Urutskiev producing ball lightning, producing monopoles, which are themselves apparently the pseudo-monopoles, magnetically excited neutrinos and neutrino condensates. And they have been proven, and that the heat that generated in those Taylor cones, or the cones that are naturally on that PNK02 carbonyl nickel, gets to sufficient energy by at least Argonne National Laboratories belief, and by Messiat's going all the way back to 1996 to produce the structures that are able, the neutrino and antineutrino structures that are able to go and transport matter as observed in the Lion reactors and other reactors, and in Hutchison's work and Ken Shoulder's work, and so on and so forth that we've talked about for so long. And so there's a whole bunch of data points. This is cold. This is cold. And I'll play this once more because this is explained by Solin. Explosive quantum coherent reaction due to the loading. Now you could argue that it is putting hydrogen isotope on there and whatever other things we've discussed, but anyway, these beautiful instantaneously produced crystals which are open, and that is explained by the Russian patent from 1992, which we have here. Due to the implementation of coherent ultrafast explosive crystallization, it consists of many fragments and dispersed areas in the form of ordered clusters and microcrystals which are separated from each other by voids. So I think probably that explains Rossi's early work. I think the lithium might only be employed in this means by having I don't think the lithium aluminium hydride was mixed with the nickel, and we proved in Bang that the lithium aluminium hydride forms and envelops the nickel, and with many cycles of experimentation. And Parkhomov, I discussed this at ICCF 22 when I was asked the question, because I think it was Peter Hegelstein that said, is he using lithium aluminium hydride and nickel? I said no, and I explained in that answer that he found that the lithium aluminium hydride melts and breaks down, but it wets the surface of the nickel, and it doesn't produce any excess heat. And that was very important to understand, because we had also observed that in Bang. So if you go to the MFMP's YouTube channel and type in Bang, search for Bang, you will see the event, and if you follow that story, you will see that it was actually Edmund Storms looked at that material under SEM and saw that it was covered. It was basically all of this dendritic goodness, this spiky loveliness that I believe is the exact reason this stuff works, was not there. And I believe that the lithium aluminium hydride was doing just like they've been doing since the 1940s with titanium hydride, and it was just acting as a pill to release hydrogen into the cell, and when it cools down to capture it back. And the hydrogen is adsorbing to the surface and promoting the production of ectons, which are evos. And so every data point is lining up to explain this with relative ease. And so it does not matter that it melts. And so I think that's basically it for that. And now you will always get reactors destroying themselves, but if it runs for 7 months, then you could run it for 6 months, and you have a device that produces excess heat for 6 months, and that's good. And there was only 1.6 grams of nickel in here. I think it was the tungsten that was providing a lot of the heat, and maybe the silicon carbide. But the whole thing, the active agent is these coherent matter structures, whether you're talking about the coherent matter of combinations of positrons, electrons, and neutrinos, encapsulating and interacting with matter, as you're talking about with Takaaki Matsumoto, which is ball lightning or micro ball lightning, or you are just talking about
you can't get a scenario, in my view, where you've just got pure electrons. You can get pure electrons to cluster together, but because they will be emitted by something in an environment, something, they will interact with neutrinos, even relic neutrinos in the environment. I'll talk about that with some really important really important data point in the future. These things then go into the metals, and just like they did in Pientelli, just like they did in Suhas-Ralkar, just like they did in Lion, just like they did in SV Adamenko, and they can act and continue to act over a long period of time. Okay, so I've worked from the bottom. Hey Bob, have you studied the holes in the ground in Russia? They could be evos by the pictures. No, they're not. I think they are methane hydrates or methane that's trapped, and when the permafrost goes, there's some good explanations for what that is, and there's some scientific studies on that. But it's an interesting phenomenon. I wonder if the holes forming in the ground. No. Hey Bob. Yes. Okay. So I have seen those. One of those 3D Vega samples has a spot that really resembles Tycho crater. Oh, when I go through those images that I've been sharing, and bearing in mind you're just seeing a 4K image of it with relief on, the images they're at least 4 times that dimension in terms of resolution, and when it's creating 3D images, it's making JPEG, so that there's some loss in fidelity. So the actual images themselves are far higher quality, and you can see hexagons, you can see every form of well understood exotic vacuum object structure. You can see on the Vega Valley. It's got the whole lot. It's got the whole lot on one sample. Anything that can do coherent matter can participate in these kinds of reactions. So I like to work with what I can see and what makes sense. So in this case, Cooper pairs can form when you get bunched electrons. There are bunched electrons in here. Cooper pairs can then condense. That forms coherent matter. Those things themselves can produce superfluid, electron condensates, as Shoulders refer them to them as, and they're superconducting. That produces intense magnetic fields because you've got toroidal and poloidal fields, and that because they're negative until they lose their expressed charge by balancing with ions and so on. They will pull in ions and so forth. So they're a self-organizing thing, and they organize themselves very, very quickly. Electronic objects that build at electronic speeds. Sound drops intermittently. I wonder if it's just heat. It's just so hot here. It's just so hot. Maybe if I turn the air conditioning on, I'm sorry. Hopefully it's recorded all. Okay. I'm going to turn, maybe it was clipping, I don't know. Okay. Okay, so if the sound was dropping at any point, is there anything that people think they've missed? I think the concept is really simple, what I've described here today, in answering how could it get started and then keep running even after the nickel melted. I think I've answered that pretty darn thoroughly, and it gave me the excuse to introduce Messias to the community, at least properly. I know I've mentioned him a good number of times in passing, but finally.
So self-healing, self-smoothing. So you could do what Tesla showed, and what's in this 2013 work by Messias, which is to use liquid coverings for your electrodes. So the idea of using liquids was first done by Tesla, then, well, actually it's actually normal electrical devices before, but in terms of producing electrical particles of matter, something very close to exotic vacuum objects or ectons, it was really done by Tesla first, in something that can transport a vast amount of energy into a very tight beam. Then Ken Shoulders had it in his patents from the late 1980s, and then you have thing. But this PNK02 nickel is so cheap. It's so cheap. And like I say, you would only need a little pill of titanium hydride in there, as described in this 1980s book, completely patent free. And how I've described this, I mean, in my view, it is how it is. And then what you do is you have secondary things that are very good at producing vast amounts of energy. And one of those secondary things, I would say, is tungsten. And whilst the energy calculations that I gave at ICCF 22 were for the amount of nickel, I was arguing that it was silicon carbide. And I have spent a lot of time, in fact, the early numbers of presentations in my remote view blog was focusing on tungsten as the energy source, and I've shown that with Amasa gas as well, and what you get produced. And so I think Mizuno's potassium carbonate in water and tungsten electrode, which they had their Mizuno singularity where it exploded, and they had a claimed COP of 800 times the energy input because of the rate at which the rate of change of temperature and so forth. That was the tungsten. It was the tungsten and the exotic vacuum objects that were interacting with the tungsten. It just did what you saw in I talked about with David Hudson. He experienced it twice in the, I think, 1980s, and talked about it, I think, 1994, and then Mizuno, I think, in 1996 or sometime around then, and then other authors. But the first one was Irving Lamure in the 1910s. I think Sapphire was in 2017 that they observed it, and we observed it, and repeatedly did it. I believe in Vega experiments in 2020. So I don't think you need to overcomplicate this. I mean, it is what it is. I think what I think is the way to go, and I think you'll find that is the way I go, is to focus on making a coherent matter structure where you can feed it and it's not touching anything, because and it's stable enough so that you can work within a certain domain where you are just capturing the energy that is released by the condensation of the matter. And then periodically you need to break it up, because you kind of don't want too many electrons to condense, because if they destabilize and regain their charge, then they are going to blow up, and they're going to blow up with some almighty intensity. And that I have discussed in reference to the fluidization of electrons. There is a paper that was presented or made available by Ken Shoulders. So you kind of want to make and break. It's been a theme for a long time for me. You don't want to keep building and building and building. Okay, so it's 20 past midnight here. I'm going to put another shout out. Please, I don't normally do this, but like the video, share it, because I think this This video answers, in my view, very clearly and with exact references to processes, means and methods that have been known since at least the 1980s, but possibly as clearly as the 1996 paper by Messiatz, about how you do all of these kind of Lena experiments and what are the key factors. It's all in there, really. It's all in there. What I've done today in terms of generating heat. There's almost nothing that can be patented that actually has any meaning. The only way you can probably get away with it is to be either blissfully ignorant and have incompetent patent adjudicators, or to lie. Those are the two options I see. Because liquid electrodes have been done, high current discharges in short time frames have been done. The reasons why that does what it does has been well described. The things that they produce, which are observed and have been observed by many people independently, are the same things every time, and they have certain parameters which they can do. And one of the beautiful things that they can do is stabilize radioactive material, and that is why I'm focused on that. And so, use the fact that it likes to reorganize matter, but tends to like to reorganize it to stability as a tool. Use that God-given tool in a way that benefits humanity. And yes, other countries are dumping a lot of tritium from their reactors. It's one aspect of the waste that comes from reactors. But we shouldn't use the reason that other countries have dumped waste as a reason to say, let's just continue doing it and let's do a lot more as we build more nuclear reactors. No, let's fix it. Let's find this and deliver this solution. And then we can use the same understanding to fix the other more toxic waste that is produced. I think embodiments and designs of working embodiments would be valid, but I think what's important is to get the clarity of understanding of what is going on. It is not a coincidence that SV Adamenko's reactor from Proton 21 went to the state and then went to, I think, Brookhaven National Laboratory, and they are trying to create a fusion device from it, right? Okay, so they've accepted it. Here you have Argonne National Laboratories pretending that with all their research from the Department of Energy and blah, 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 that they're managing to rediscover what was given in a paper in America in 1996, which, by the way, the person was told at that conference that what he was talking about was essentially exactly what was already patented in the previous decade by Ken Shoulders, having studied the work of John Hutchison, who was studying the work of Tesla. That's what I can say. Okay, so yeah, thank you. That's it. I'm probably gonna. It's too hot in here for me now. So I'm going to thank you all for your time. And yeah, if anyone's got any space in the UK, let me know. Just send a message to, quantumheat.org through the contact form there. And maybe I can have an ale or two with some people in the UK. I'm going to be getting access to a number of Hutchison samples, and hopefully get some look at those and be able to share some macro photography. Some of these samples are absolutely stunning, and so they were dispersed to the winds, but it would appear that the winds have are giving me the opportunity to look at them. And there's some other things that it's quite magical that I'm gonna hopefully get some footage of. In Scotland, I'll give you a clue, in Scotland. And hopefully I will be able to share that with you. It's something I've been carrying for quite some time, and it's part of O-Day. But I want to get some really high quality visuals of these things
as part of the presentations there. So thank you very, very much, and I will see you. Good night. Dobronoc. Arrivederci. Why did I say that? Bonne nuit. Buenos Aires. Catch you later.